telescopes which have large apertures. So he understood aperture averaging. But what I really like is his explanation that long telescopes, meaning big telescopes with long focal lengths, may cause objects to appear brighter and larger than short ones can do, but they cannot be so formed as to take away that confusion of the rays which arises from the tremors of the atmosphere. This is 1704. Pretty smart guy. And that's a really good explanation of what's going on. And let's just look at that in a little more detail. So if we have a perfect optic, and here I've drawn a simple lens, and of course, you know, if it has any useful characteristics like field of view, it takes more than one lens. But the size of a spot from a plane wave that enters this perfect optic is not an infinitely small spot as it would be for geometrical optics, but it's slightly enlarged because of diffraction. This is light at the edges of the aperture which get bent slightly. And so you get a spot, a finite spot, and that spot is related to the focal length of the lens, the wavelength, and the aperture diameter, f lambda over d. So if I want more resolution, I can make the aperture larger. If I want to make the spot smaller to get higher resolution, I can make the aperture larger. I can, if it's appropriate, make the wavelength shorter. And I can get as much resolution as I want. If I could build a really big telescope in space, that'd be the thing to do. But when you're on the ground looking through the atmosphere, which is a region of different temperatures in the air, you have this situation. So here comes our plane wave, which has been traveling through the perfect vacuum of space for, say, 13 billion years. In the last millisecond of its journey, it goes through the atmosphere and gets totally screwed up. Because what happens here is air, when it changes temperature slightly, has a different refractive index. And so the speed of light slows down in areas where the index goes up. And so now the phase of the wave gets distorted. The one part of the wave gets behind another part. And so it becomes bumpy. And in a very complex way that changes very rapidly, hundreds or even thousands of times per second. It's different every millisecond. So when we try to focus this messed up wavefront with our telescope, we get this big blob back here, and now our resolution is no longer governed by how big the telescope is. It's governed by this parameter we call R0, which is a characteristic of the atmosphere. And it's like an equivalent diameter of a telescope that gives us a perfect image. And typically that number is for the best astronomical sites in the world, like on top of mountains in the middle of oceans. It's like 15 to 25 centimeters. So if I have, even if it's 30 centimeters, a 12-inch telescope, that's the most resolution I can get on the Earth. If I make my telescope bigger, I don't get a better image. I just get the same blurry image, only I get it faster. So, 250 years later, a guy named Horace Babcock at Palomar Observatory suggested an approach to correct this problem. And this is a very interesting paper. It was published in October of 1953. And it has all the ingredients in it for adaptive optics, what we call adaptive optics today. And you know, it has a way to measure the distortion, and it has a way to actively correct it. They were trying to use a thin film of oil on a mirror that they charged with electrons to change the thickness of the oil. And it was something, a device called an iodophore, and it was supposed to be used to project television outdoors. Never worked, and the technology just didn't support the idea. So here's the idea. If I have a wavefront, now this is very simple, right? It has a step function in the phase, but then I have a mirror that has a notch cut out of it that's half the height of the distortion. If I line it up perfectly, you'll see that the leading edge here gets reflected first, and it catches up with the rest of the wavefront just as it meets the main surface of the mirror, and the reflected wave leaves with the distortion removed. So in a system where there's two-dimensional distortion that's changing, I need a thin mirror that I can change the shape of. It was originally called a rubber mirror because, you know, it's flexible. Today we call them deformable mirrors. And there's these little pistons underneath that push and pull on the surface of the mirror to change the shape. And it only takes a few microns. 5 to 7 microns of stroke will completely remove the distortion introduced by the atmosphere from the vacuum of space to the ground. So you just need to figure out what this bumpiness is, line it up perfectly with this, then, you know, change the mirror to match, put the opposite of that on there, so that when it gets reflected off the mirror, it removes all the bumps. And now I have a wavefront that's equivalent to what it was when it entered the atmosphere.
Easy problem.
No
Easy
problem.
Didn't you say that there's changes maybe on the millisecond
Yes.
level of the incoming
Yes.
disturbed?
Correct.
So how do you sense
Good
what that
question.
is? And then,
Did you pay him good money?
Yeah, so that's part of the problem, right? And I'll talk about that a little bit here and give you some feel for that. So the way this would be implemented in a real telescope is up here is your object of interest, and you know, astronomers call these guide stars, or, you know, if they're actually making a long image, they have another device that keeps the telescope tracking that particular star, which may be bright enough to do that. Or it could be the actual object itself, if it's bright enough. And that's the key here to one of the issues. So then you, normally you would just get this aberrated image, but now if I relay the aberrated image through an optical system, and I have a beam splitter here, a sampler that can pick off part of the light, and then I have something we call a wavefront sensor, and, you know, there's a computer here, and then I have my deformable mirror. And so what I need to do is analyze in a very short time, and systems have been built that sample the distortion in the wavefront at, say, 10 kilohertz, 10,000 times a second. And, you know, that is then filtered in a control system, passed to the deformable mirror, and some fraction of that error is used then to correct the distortion. And so if the distortion is changing at 1 kilohertz rate, the way the controls mafia guys do it, you know, is they have to sample at a much higher rate and then only correct part of it, or otherwise the loop becomes unstable and so forth. So that's typically what happens. If you want to have a 1 kilohertz closed loop system, you need to sample at like 10 kilohertz. And so that takes a fair amount of light. And so you have to have a pretty bright object up here, because you're only picking off part of it here. The rest of it goes to your camera. So here is an animation of how this works. This was put together by Gemini Observatory. So here comes light from the telescope. Here's the deformable mirror. Here's the beam splitter. And we'll see the distorted wavefronts coming in. They get sampled, analyzed. We close the loop. The mirror starts changing shape, and all of these distorted pancakes become flat, and now we get a corrected image.
Amazing.
Amazing. And so here's what that looks like for real. So this is the image from the 3.5 meter telescope at the SOR of a star, and when the loop is closed, you see what happens. I'll try to walk you through it. The first part here is the track loop is open, the track loop is closed, and then the higher order loop is closed. We typically correct tilt, the overall motion of the wavefront, with a flat mirror that we actuated 2 axes, X and Y. And so what we see in this example is, this is really 2 stars, a binary star, and these are a 1/10 of an arc second apart. You know, an arc second is 5 microradians.